The neural network, which we also refer to as the artificial neural network, in our case, a basically attempt to reproduce or to imitate the type of nonlinear learning that occurs in the networks of neurons found in the brain of an individual. That's what it does. And normally, it is a model that is used for the purpose of classification or forecasting or estimation. And it's a very helpful model because generally it is known to give very, very good results. It's very good forecasting, very good results generally compared to many other models. So we will try to understand a little bit what this neural network is about for our case. But before we get into that, it's also always good to have an idea of how a neuron is in the human brain. A neuron is something that is a little bit like this. Normally, you would have dendrites, you would have a cell body, you would have an axon. And what happens is that signals, informations are being received through the dendrites into the cell body, which is going to process this information. And the processing will make it in such a way that a inform after having reached a certain threshold, uh, the signal is going to be fired to another node. A signal will be fired to another node. To another node means to another cell. And the procedure repeats again and again. So I repeat, informations are received from other cells, from other cells through the dendrites, which is received in the cell body, which is going to process that information. And after having reached a certain threshold, this neuron will fire a signal to another node. And what we try to do in artificial neural network is to imitate a little bit what's going on there. And how do we do that? Informations are received through our input variable, through our feature space. Informations are received through um, a through our feature space and are combined into a single value. They are combined through a single value through what we call a combination function. They are combined through what we call a combination function. And when they have been combined through a combination function, they are going to be processed again, uh, where now this input that we got here will be passed on into something that we call an activation function. We'll pass on into something that we call an activation function, which we are represented like this. We're representing like this. And when it has been gone through an activation function, what is going to happen, it will produce an output. And this output is like the signal being fired. And what is going to happen, this output is going to be the input now for another node that will come in. And it will go on like that. So you have a series of neurons that are connected with one another and making a network. This is the idea basically in the neural network. We will get into this again a little bit more in details later on. So, but in a very quick introduction into what a neural network is about, we're not going to get into the biology of neural network, but the idea here is that inputs are received into a node. We refer to that as a node, which is like the cell body, a node. And that node does two things. Number one is that it combines these inputs. Number two, it processes these inputs into what we call an activation through an activation function, and the value that you obtain from this activation becomes what we call the output, and the output is going to be the input now for another node again. So just imagine having different possible outputs all connecting to another node, creating a series of network. So that's a little bit in a nutshell what this is about. Of course, there are advantages and there are limitations as well. So, but one of the advantages of using neural network is that they are quite robust with respect to noisy data. Okay, because network contains many nodes and normally these nodes, they have what we call weights assigned to each of them. They have weights assigned to each of them through what we call the constitute a connection. All right. Now, maybe without much further ado, I'll get into the details, but just bear in mind something. Even though the neural network constitutes a lot of advantages, there one of the main advantages is that it is robust with respect to noisy data. But the main disadvantage with the neural network is that it's considered sometimes as what we call a black box method, because we don't really see what's going on inside, and we sometimes have difficulties in understanding sometimes what's going on. Let's suppose if I talk about, let's take a simple example. If I talk about multiple linear regression, you have y is equal to beta node plus beta 1, x1 plus beta 2, x2, and it goes on like that, plus epsilon as opposed to beta p. Now, these estimates that you get, beta cap 1, for example, the estimate that you get here, this estimate is something that you can understand, that you can interpret, that you can make sense of in a case of multiple linear regression, because it abides to certain assumption, and you can go and interpret what this beta cap 1 represent. You can also know exactly how it has been obtained mathematically. However, this is not the case in the case of a neural network. In the case of a neural network, things are not like that. The weights that I was mentioning earlier, they are not obtained in a way that they are not obtained, the optimal weights in the neural network, they are not obtained in a way that makes it easy for us to understand what these weights necessarily represent. This is why the neural network is considered to be relatively opaque to human interpretation. You use it, it gives you very good forecasting, it gives you very good estimation, but in the end, it stays somehow opaque to human interpretation. That's the main disadvantage of a neural network. Now, when I'm talking about these weights, you might be saying, what am I talking about? I will come into that later on. All right, but before I get into that, you have to understand that before you apply a neural network, your data needs to be prepared well. It has to be prepared before you apply the neural network. The one possible drawback of a neural network is that all the attributes must be standardized, okay? Taking values between 0 and 1, for example, okay, even for the categorical data. This is one of the things that you need to do before you apply a neural network. This is what we refer to as the input and output encoding. We have to basically transform our data set in such a way that one particular variable do not dominate the analysis. Otherwise, what would happen is that because of the issue of scaling, if you have, for example, x1, which of you have x2, these are the feature space. Let's suppose you have up to xp, and let's suppose x1 are values that range from 10 to 100. X2 are values that ranges from again 10 to 100, things like that. But let's suppose you have a x7 are values that range from 1000 to 1 million. You have a problem then, because if you have values that range from 1000 to 1 million, the range of values are already high. The range of values is already high, which means that there is a lot of variation, number one, and you are dealing with a large scale here. What is going to happen is that if you take that data as it is and you put it in the neural network, this variable x7 will dominate the analysis. And it's not a very good thing. So we want to make all the data be, like all the variables on the same scale. We want to make all of them to be on the same scale so that one of these variables do not dominate the analysis in any way possible. And this is why we are going to use the 0, 1 output encode input output encoding. All right. What does this mean? That we are going to convert all our data, all our in feature space the whole feature space and also the target variable into zero, into values that are between 0 and 1. That's what we want. And to do so, we have different ways of doing it. One of it is through the min-max normalization. The min-max normalization, if you have a set of values, all right, if you have a set of values, let's suppose x1 takes different possible values, like you have 1, 3, and then 5. And min-max normalization, what we will do, or let's suppose you have, make it simple for us. Suppose you have 2, 4, and 6. The min-max normalization, what it will do is that it will convert this. How does it convert this into a new set of values in such a way that this 2 will become 0 and the 6, let's suppose you have only 3 values here, this 6 will become 1. And what will happen to the 4? The 4 will become like you take 4, you subtract the minimum is 2, you divide by the range. The range is a maximum, subtract the minimum, which is 6 minus 2. So you have 2 out of 4, which is, of course, half. So this becomes 0.5. So the 4 becomes 0.5, the 2 becomes 0, the 6 becomes 1. Um, this is what we do through min-max normalization. So for the continuous case, it's pretty straightforward. That's what you have to do to apply the min-max normalization. However, for categorical data, it's not that straightforward. Mm, what you can do is you can create what we call dummy variables, all right? And basically, if you have a data set like, let's suppose gender, you have male, you have female, you have male, or you have female, you have male, and so on. What we do here is that we create a new data set which is male. You won't have male anymore. This will become 1, this will become 0, 0, and every time you have male now it will become 1. So you don't need to create another uh, indicator variable for female. All right, this is one of the things that you need to bear in mind in the case of what we call a dummy, creating dummies. If you have male is represented by 1, automatically female is represented by 0. So there is no need for you to create another one female where this is 0, 1. There is no need for you to do that. Okay, only one of these indicator variable will be sufficient. So this gives you an idea that if you have two levels in your categorical variable, if you have two levels, you will always have only one dummy variable. If you have k levels in your data, in your in your categorical variable, then you would have k minus 1 indicator variable, or k minus 1 dummies. All right, that is how you generate these 0 and 1. Like if you have red color, let's suppose you have color. Let's suppose you have color. You have red, blue, green, and green again. You have only three colors, I suppose: red, blue, green, green. So what happens is that if you want to create dummies, you will create dummies, for example, for red, and you will create a dummy for blue. There is no need then for you to create a dummy for green. So red would be taking values of 1, the rest will be 0. And blue will be taking a value of 1, the rest will be 0. Then automatically, it is quite logical to understand that the other one, that is the green color, would be for these last two records. So there is no need for us to create another one, which will mean that this is 1 and 1. No. So this is a little bit for the case of input encoding. For the case of input encoding, that's what we do. For continuous data, we are going to refer to the, for min-max normalization, we are going to apply the min-max normalization. For categorical data, we are going to apply, we are going to create indicator variables, as I said. So that's the first thing. But what about the output now? The output is also very important. It's a little bit more tricky here. You have to be very careful. When we talk about the output, there are certain things that you need to consider. One other thing that you need to understand is that the output, when we talk about the, um, you remember when we talk about the neural network, there is a series of inputs that are processed through a node, all right, through a combination function and an activation function, and this is um, an output is obtained. Now, this output is what? The output node that the output that we get, the output that we are going to obtain, how do we want it to be? It's always going to be, if we are doing min-max normalization, if we have been combining and our data, if we have been encoding our data from 0 to 1, we would expect to have normally the output to be between 0 and 1 as well. We want the output to be between 0 and 1 as well. Now, if it's going to be between 0 and 1, we have to be careful. The question is how we're going to interpret that output. For a dichotomous classification, like if you have an output where you have only two possible solutions, which is one leave and one stay, one of the ways of doing it, if you have an output where you have one leave and one stay, one of the ways of doing it is to create only one output node, all right, instead of several output nodes. But the value that you will get from that output node, the value that you will get there, will have to be, you will have to sort of a priori determine it. What value would constitute stake? What value would constitute leave? You need to determine a priori the value that you're going to receive from the output. What is it going to be? If you decide, for example, any value that goes above 0.67 would be considered as out as leave, and any value that is less than 0.67 would be considered as stay. Then this is how you're going to classify an output as whether it's going to be leave or whether it's going to be stay. The value that you're going to get there will determine whether this result will be a leave or the result will be a stay. What I'm trying to say here is that you need to set this uh, before you do the analysis. You will have to set this normally. Now the question is, how do you set this? This is where it's a bit tricky. It's a little bit of a trial and error basis here. It's not something that is straightforward. You can't come and say, for example, if a value is greater than 0.5, it's considered as stay or it's considered as leave. No, you have to play with it a little bit here. For example, we decided for the case of leave if output is greater than or equal to 0.67. So an output of 0.72 would mean that the record is being classified as leave. An output of 0.5 would mean that the record is classified as stay. But the thing is, how do you determine that? As I said to you, it's not so straightforward. At times you have to play with that. If you have set it as 0.67 and you have set it as 0.67 as an out as a threshold, you might have to play with this. And for example, if you see that 0.67 is not giving you a good result in the end, you might have to play with it and make it become 0.5, or you might have to play with it and change it to 0.4 or something that gives you a relatively good result, because otherwise, you would be wrongly classifying outputs. If you wrongly determine this value of 0.67, you would be wrongly classifying your output, and this is not what you want. So it's one way is to do it like that is by setting it a priori. Okay, all right, which means you don't have any knowledge about what's going to happen, but you already set it, and then what happens is that you see what result you get. And if the result is not really very nice, you see that you are wrongly classifying records too much, then you would have to adapt this value and rerun the neural network accordingly. Okay, so that's one way of doing it. That's one way of doing the output encoding. There is also another way of doing it that I'm going to get into later on. There's another way where you can, instead of having only one node, you can have two nodes, but I'm going to get into that later on. But for the case of output nodes which are ordered, this is relatively easier. For output nodes which are ordered, like when I talk about the dichotomous output, I'm talking about gender, for example, male and female. You want to predict male, you want to classify male and female. This is a where the issue arises. You can't have a specific value of 0.5 where you are going to say if the value is greater than 0.5 it is female, if the value is less than 0.5 it is male. You can't do that. This is why you have to determine this in a way that is a little bit um, trial and error. But for cases where the data is ordered, like you have first grade reading level, second grade reading level, third grade, and fourth grade, then you can easily encode the data like this. For example, if you have 4 grades, you can say that if the output is between 0 and less than 0 to 5, then it is classified as first grade. This becomes relatively straightforward for this one because there is no problem because you would have already encoded your data. Uh, you would have already encoded your data, like if you have first grade, second grade, third grade, fourth grade. If you have first grade, second grade, fourth grade, what happened is that each time when you would encode the data, for example, the encoding of 1 would be 0, the encoding of 4 would be 1. So any value that is close to 1 when you are predicting later on, any value that is close to 1 will of course be predicted as 4. This is why we say that any value which is above 0.75, if we put it as equally um, distributed, any value that goes above 0.75 will be predicted as what? As a 4. Any value that is close to 0, that is a value that is less than 0.25, will be predicted as 1. So, because you have to understand that when you are getting the output value, you're not getting 0, you're not getting 1, you're not getting 0.25, you're not getting 0.75, you're not getting 0.5, there's specific values. All right, you're not getting such type of things. You are going to get a different set of values which can be even 0.11. It can be any kind of values. This is why you need to determine what is going to be the 0.11. Will it be classified as a second grade? Would it be classified as a third grade? So if you get 0.11, logically, the fact that it is close to 0, but it is close to 1, and it is quite natural to say that it should be classified as a first grade. So we determine it by creating intervals of this sort. If it is ordered, like in this case, we can create these intervals like this. 0 to 0.5 is first, 0.5 to 0.5 is second, and so on. So that's one way of doing it for cases of um, output that are ordered. All right. So here we've just talked about a single output node, But we have case where you can also have more than one output node. You can have two or more output nodes. Like in the case of marital status, like in the case of color, gender, and so on. Then if you have a case of marital status, having a single output node is not a good idea at all. You can't have a single output node because if you have a case of marital status, let's suppose you have someone who is married, divorced, single, separated, let's suppose things like that, a married, divorced, single, separated, widow, whatever it is. Now, what happened is that you can't imagine to have a single node and from that single node to create intervals from 0.00 to 0.25. You will say that it is married. You can't do this kind of thing. It's very, very difficult and impossible. You won't be able to do it at all. For dichotomous output, it is okay. You can play with the values as we explained above here, all right, 0.67, things like that. But here it's not feasible, it doesn't make sense at all. So then this is why for such type of cases, you will need to have several output nodes. All right, you would have to have a several. Let's suppose you have only these three marital status: married, divorced, and single. Then you will need to have three output nodes, and you would have all the three output nodes will be containing a certain value. Let's suppose you have 0.1 here, you might have 0.9 here, you might have 0.7 here. Then if you have for this is for married, this is node is referred for the divorce, and this node is referred for single. All right. So if you have something like that, if you have predicted 0.1 for married, married, 0.9 for divorce, and 0.7 for single, then logically what you would say is that your classification is classifying someone as divorced because it has a higher value for the node of divorce. So in this particular case, instead of having a single node, as I explained earlier, you would preferably have several output nodes, not one output node, but more than one output node. By the way, you could also apply that for this case. Instead of having a certain threshold that is a little bit tricky to determine, you can also do it like create two sets of nodes, two nodes, one node for leave and one node for stay, and then you will see which one gives you the higher value. And the one that gives you the higher value is the one that you're going to select as the classified records. If it is stay which has the highest value, so you classify the record as stay. So that's how you do the input and output encoding. So maybe you might have to take a pause here and just rewind and try to go through what I just said again, because there have been different things that I've discussed. There is one which is the input encoding, which is through the min-max normalization and dummies. There is one which is the output encoding. Now, by the way, your data that is your target variable will still be encoded through 0, 1, either through the min-max normalization or through a dummy variable, whatever it is. But in the end, what I'm trying to say here is how you're going to determine the whether that record that you have should be classified as a certain as leave, or whether the record should be classified as stay. This is where you need to apply a threshold if you are using a single node, or if you are using more than one node, then you need to check which one gives you the highest value. And also for the case of an output node which is ordered, then things are relatively straightforward. There is no issue at all. You can just um, create intervals as we did here. So this is a little bit about the input and output encoding. After having done this in your data, that is created your done your min-max normalization and so on that you required, and also determine whether you need to have one node or two nodes or three nodes for the output, things like that, and also determine what are the threshold value that you will use for the output encoding. After having determined all these different things, now we can get into the context of what a neural network is. How does what is a neural network basically? What is it? What does an artificial neural network look like? So, as I said to you, it depends, not it depends, but it imitates rather the neural network that we have in the brain of an individual. Normally, you will have a series of nodes that are going to be connected, and this will constitute a network. And these series of nodes there will be found in different layers. All right. Normally, you have first of all a series of nodes that refer to the input layer, and a series of nodes that we refer to as the hidden, which are going to be referred to the hidden layer, and a series of nodes that will be referred to the output layer. So there will be nodes that will belong to the input layer, there will be node that will belong to the hidden layer, and there will be node that will belong to the output layer. Input layer is very straightforward. You already understand the term itself. Input means you would have nodes that constitute your input variables. That is your feature space. The output layer would be nodes, whether you would have one or two, depending on the encoding that we just talked about. The output layer would be that layer that will contain nodes, or only one node or many nodes, uh, that will give you the predicted output for your result. And then in between these two, hidden layer and output layer, you would have either one hidden layer or more hidden layers. All right, and hidden layers will consist of hidden nodes in it. So, And you would also have all these nodes, input nodes, output nodes, hidden nodes will be connected through what we call weights. And this is where we get into what a neural network is. Through a diagram, let's have a look at the diagram and you will see what it looks like. You have the input layer, you have the hidden layer, and you have the output layer. So the input layer constitutes of nodes. For example, that node might be referring to variable x1, that node might be referring to variable x2, that node might be referring to variable x3, and so on. And suppose you have only three variables in in your data set. You have all these different nodes here, and which each of them will refer to one particular variable. And what is going to happen is that these will be connected to something that we call an hidden node. And this inner node will be connected to something that we call an output node. But bear in mind something, this is a simple neural network architecture. But you might have more than that. You might have one hidden layer and another hidden layer. Then these node will be connected to another hidden node, and the hidden node in the end will be connected to an output node or more. So as I said here, this is a simple one. This is a simple architecture showing you only one output layer, two hidden nodes in the hidden layer, and you have three hidden input nodes here. But things are more obviously more complex than that. Now, what is going to happen here? The X1, there is no processing. In the input layer, there is no processing as such. When we refer to it as a node, we are not going to do any combination or activation as we would do in other nodes. We would not be doing any of these things here. These nodes just contain values, that's all. For example, if you have a data set, you have x1, you have x2, you have x3, and then you have your output, which we are referring to as z, let's suppose, in this particular context. You have record 1, record 2, record 3, and so on. So for that first record, this is what we are referring here. To that first record, you would have a set of value for the first variable, x1. You would have a second value for the x2 and a third value for x3. And then what is going to happen is that you will get a predicted value of z for that first record. Then it will happen for another record. You will do the same thing again and again. But for the first record only, I'm referring to only one record here. Look at what's going to happen. You will have a value here, a value here, and a value here. All these are going to be sent, and all these are going to be sent to one node. And then it will be sent to another node here. And when all these values are sent to that node, there will be a processing that will be done here. All right. There will be a processing that will be done at this hidden node. And that processing will be a combination and an activation that's going to happen. And combination and activation. And then this will be sent to the output node. But it will be sent to the output node. It's an output that will be sent to the output node as an input. It's an output from that node, but it's going to be an input to that node. It's an output from that node, but it's going to be an input to that node. And something else will come from that node as well as an input. You will have an input from that node where you will have an output. And the combination here and the activation here will give you an output which is going to be your final output. And this final output here is going to be determining your classification. All right. If the value is greater than 0.67, let's suppose it's going to be classified as safe, things like that. So let's get into all these details. But before we get into the details here, before we get into the details of how to run a neural network, maybe what is important for you to understand is what is this hidden layer, all right? What is this hidden layer? Determining the number of nodes is very important in the case of a neural network. Now, having got a brief idea of what I'm trying to show you here, remember that these nodes are connected by weights, all right? In fact, the weights are analogous to the parameters from a regression that you are used to, beta 2, x2, etc., etc. So you have variables that are connected by weights, and these weights are analogous to these betas that you have, the beta cap 1, beta cap 2 that you're going to estimate. These are are a little bit like the weights that are connected to these different x that you have here, and will bring you a certain value here. Bon, the next step is to understand what this hidden layer is about. The hidden layer is important because this is where normally the detection of nonlinear relationship occurs. Maybe I did not mention it earlier, and I forgot to mention, in fact, the most important thing. I'm going to mention it now. In fact, why do you run a neural network? The neural network is one model that is extremely good at detecting non-linear relationship. It's one of the models that is very good at detecting non-linear relationship, very complex relationship in a data set. This is not the case for multiple linear regression, which is based on the assumption that the data is linear. But the neural network can adapt to nonlinear relationship. It can detect nonlinear relationship very easily. And how does it do that? It comes from basically the hidden layer. It's where everything starts. The hidden layer is where these nonlinear uh, relationships within a data set will be captured. Why? Because there is going to be a processing that is going to happen through a combination function and through an activation function. It's this activation function that determines everything. It's this activation function that will capture this nonlinear relationship that exists in the data or not. Now, we will get into this activation function later on. But what is this hidden layer? This hidden layer is important because if we don't have this hidden layer, if we have only the input and output layer without the hidden layer, let's suppose we get rid of that, we have only the input that are connected to the output, then what we are doing is that we are basically applying a logistic regression. It's analogous to a logistic regression that you might have been doing in other courses. But by adding this hidden layer, you are going more than a logistic regression. You are enabling this model to capture more complex relationship that exists in the data. More complex relationship can be identified through this hidden layer. The more nodes you have, the more the data will capture complex relationship. The better, obviously, will be your predicted output. The more hidden nodes that you have, the better would be the prediction of your output in the end. This is the idea behind the hidden node because it's going to uh, learn the data, it's going to learn the characteristic of the data better. Why? Because if you think about a model, as I said to you, you have a model beta node, beta 1, x1, and so on. The more variables you have, the better would be your R squared value. The more variables you have, the better would be your R squared value. That is, the goodness of it will be high. But we have to understand something is that when you have a high R squared, that doesn't mean that it is a very good model. Why? Because having too many variables means that the model is not parsimonious. And if the model is not parsimonious, this is where you have a problem of overfitting. Overfitting. So what you have to understand is that having hidden nodes is very good because it captures complex relationship. But having too many hidden nodes is like having too many variables in a model. And if you have too many variables in a model, too many parameters in a model rather, we already have these variables. But now imagine having other latent variable as if added to this model. The more you have, the more parameters you will have. And the more parameters you have to estimate, obviously, you would have a risk of having a higher, of having overfitting. So what you have to understand there is that having too many hidden nodes is not a good idea. Having too few hidden nodes as well is not a good idea, because if you have too few hidden nodes, you might not capture the right relationship, or you might not get a good predicted result. So then this is why you need to have a balance. You need to get the right number of nodes here in a hidden layer. Now, just imagine something. This I'm talking about one hidden layer. You might wish to have another hidden layer. The more hidden layer, the more parameters you have again. And the more parameters you have, the higher risk of overfitting that happens. So what we want to do is that in most of the time, in most cases, most projects that you're going to do to work with, only one single hidden layer, only one hidden layer is sufficient to give good predicted results. It has been proven that only one single layer, hidden layer, only one hidden layer, sorry, is sufficient in giving you very good result. Having more than one hidden layer is not necessarily beneficial. So we would focus on only one hidden layer. But the number of nodes that we have is very important. How many nodes do you need is also important. You cannot have too many nodes. You cannot have too few nodes as well. You cannot have many nodes, like 10 nodes, because if you have too many nodes, you have a risk of overfitting. But on the other hand, you cannot have too few nodes because you won't study the relationship properly, which means that you won't get predicted results that is appropriate. So if you have too many nodes, what is going to happen? You will have a very good output prediction. But if you are going to apply the same thing on the testing set, what is going to happen on an independent data set? You would have too many nodes. It means that it learned the characteristic of the data very well. And if it learned the characteristic of the training data very well, it gives you a very good prediction on the training set, but it will give you a very bad prediction on the testing set, which you don't want. On the other hand, having too few nodes will give you a bad prediction on the training set and will also give you a bad prediction on the testing set, probably. So this is where you need to again play with it. It's a bit of a trial and error basis. You will need to have the neural network run for different number of nodes. Generally, in practice, that's what you do. You have to run it with different number of nodes, and when you've run it with different number of nodes, you have a look at the errors that you obtain on the training and the testing set. And you would want to focus mainly on the testing set to see which number of nodes. Is it 5 nodes? Is it 3 nodes that give you the best error on the testing set? Then you choose the final architecture of the neural network to be that number of nodes that gives you the best error on the testing set. So this is why I said determining the number of nodes is not a straightforward thing. You will need to ensure that there is no overfitting, and so that your result can be generalizable as well. Can you go through this afterward? This is what I've already been mentioning. And as I said to you, there is this important thing that we have to understand here is the two things that happen in the neural network. At the neural hidden node, as I said, in the input node, this doesn't happen, but at the hidden node, there are two things that happen. Number one is the combination of all your inputs. And number two is the activation function. This is why you see this shape here, this S-shape function, because of this function here. Now, quickly, you have your X1. Suppose you have values here, 2, 5, 3. You have X, you have weights. The weights will be generally numbers lying between 0 and 1. Let's suppose you have 0 0.1, 0 0.25, 0 0.3, 0 0.2, etc. 0 0.7, 0 0.8. What is going to happen is that at this particular node, the same thing happened for node beta, but I'm explaining for that particular node. What's going to happen? That particular node will combine these inputs into a single value here. This is why we say the summation function. Why? Because this combination I'm already explaining it to you right now, is going to happen by taking what? By taking 2 times 0.1, 0.1 times 2, plus 5 times 0.3, plus 3 times 0.7. Then all of them, this is why you have a sum, this is why we use this function sigma, which shows a sum of all these different values that are combined together into one value. So you will have only a single value for that. I don't know what value you will have. Now that value that you get here is to be transformed into a new value. This is why it is important for you to understand something. This transformation process is where the nonlinear relationship that might exist in a dataset may be captured or not. And this value that you've got will be an input to this activation function. And this activation function is going to be the result that you get from this activation function will be your output that will be an input. This output will be an input to this one. But this activation function is what? So the combination function, as I said, is just an addition that you are going through. But the combination function is what? The combination function, there are different, sorry, the activation function, there are different activation functions that exist, okay? There are different activation functions. One of it is a logistic function, also referred to as the sigmoid activation function. You have other activation functions as well. There is something that we call the ReLU activation function. You have a linear activation function as well. You have different types of activation function, but for this course, we are going to focus on the sigmoid activation function. Now, the sigmoid activation function is a very helpful function. The sigmoid activation function, that is the when you see this sigma x, it's like you have a function of x equal to 1 upon 1 plus e power minus x. Now, that's sigma is not in value that is multiplied by x here. It's a function of x. Now, that sigma x, that is this function of x, is equal to 1 upon 1 plus e minus x. So just imagine you have your x values starting from negative 1, 5 to 5. And you replace these negative 5 in here, or you replace negative 1, you replace 1, you replace all these values, and this is what you will get. You will get a function that is like this. And this is what we call the sigmoid activation function. And what is good about this function is that depending on the values of x that you have combined together, as we did, I just showed you earlier, this value that you get will have to be transformed through that function into a new value. And that transformation will be determining whether you have a kind of linear relationship or not. And this is a good thing with this activation function that captures all different types of relationship. It captures, for example, you will see through values that lies within this range, value that lies between negative 1 and 1. You have what we call linear relationship can be captured. You have values that you have here, linear relationship that can be captured from values of x lying from this value to this. You have linear relationship that can be captured. But apart from that, if you look through this part here, about this part, around this part here, you don't have only linear relationship now. Now you have curvilinear relationship that can be captured. Even here, you have curvilinear relationship that can be captured from here to here. But then, as from here onwards, you see that the relationship becomes more or less constant. So, through that single sigmoid activation function, you have been able to observe what we call linear relationship here. You have been able to observe curvilinear relationship here. You have been able to observe nearly constant behavior here. This is the good thing with that function, is that it enables you to capture different types of relationship within that data. So using that activation function is a good idea because it enables you to capture these different types of relationship, whether linear, curvilinear, or nearly constant behavior in the data set. So here the value that you got, as I said here, this value that you got will be your value of x that you are going to input here, and that value of x will give you your output. So applying this function gives you your output variable here, will give you your output value. And this output value that you get here becomes the input for that node now, and that node will be with the combination that you have from the other node will constitute uh, a single value, and this single value would be a applied to this activation function again, and this activation function will constitute your final output. That's a little bit what's going on behind. So we'll try to investigate that through a neural network like this. And we are going to investigate the example. We are going to apply the combination function that I just explained. We are going to apply the activation function as well. Okay, we are going to apply the combination function, and the combination function we are going to call it a netj, and then we are going to use that netj as our x to this, and then this becomes your output. So what we have to do here is to have a look at an example where we are going to consider a an example, okay, where we are going to consider a particular set of value. Excuse me. We are going to consider an example here. Here we go. This is the example that we are going to consider, and we are going to try to obtain the output through a first pass of a neural network. We are going to predict the output through a first pass of a neural network using this particular example. Okay, now I've done something for you just to explain it to you. You have all these different information. I've done it through the diagram just to show you how it looks like and how you get the predicted output. Just bear in mind that you have all these different values. These represent your inputs. These represent your weights, and you have these different weights, some of them which are constant weights, like these W node A, W node B, and so on. They are not connected to any node, they are just constant. It's like in a model, in a model you have Y is equal to beta node plus beta 1x1, you have plus beta 2x2, and so on. So this beta node is a constant in the model. So it's a little bit like that. These W's are like these constants, all right? And all the others are weights connected to some nodes. So they are things like that, betas with x and so on. But what I want to show you here is how do you get the first output? How do you get the output through a first pass in the model? The output for a first pass in the model. So let me just show you this. All these different information that you have here, maybe I'll just show it through here. You will see that you have these different values. You have x node, which is 1. Each time for a constant, you are going to consider it as 1. It's going to be always 1. Even if it's not mentioned here, it's going to be 1. And then you have x1, which is 0.39. So the node x1, that is the input node x1 is 0.39. The input node x2 is 0.19. And the input node x3 is 0.68. Then you have these different weights, that are connected to these different nodes. For example, you have a node that is connecting x1 to node A. Node A represent your hidden node. You have x1 connecting node A. Now, the x1 connecting node A means you have W1A1 A. What W1A is 0.61. Then you have node X2 connecting node A, so you have W2A. W2A is 0.80. Then you have X3 connecting node A, you have W3A, which is 0.58. And then the same thing happens for the others. You have 0.8, which is a node connecting X1 to B, which is W1B. 1B is 0.87. Excuse me, 0.87 as you see here. And this is 0.79, which is W2B, and 0.45, which is W3B. Then you have the nodes that connect your hidden node with the output node. The output node is a final one. So the weights that connect the output node A to the output node, we are calling it Z, is the WAZ. So here we have WAZ, which is 0.9. And the node connecting node B, that is the hidden node B, with the output node Z is 0.9, which is WBZ, and it is 0.9 here. So this is how we have these different nodes. And then, as you would note, there are also these different weights here, which are not connected to any node specifically, which is 0.5 here. You have 0.5 WAZ, and you have for W node A, sorry, for W node A, you have 0.5. For the node B, you have 0.72, which means 0.72 is there. So what do we want to do then? We want to now combine all these different values. So originally we don't have this. This is not there. Let me just hide them for you, for example. Just add these values for a moment. Originally, you don't have these values. Let's just maximize that a little bit. So this is what we have originally. So what do we want to do? We want to apply the combination function to combine these inputs together, and then get and use this function as an input to the activation function. All right, that's basically what we want to do, as I said here. So how are we going to do this? Number one, we have to do this combination function. The combination function is we need to take 0.61 multiplied by 0.39 plus we have to take 0.19 or 0.8 rather times 0.19, 0.8, oops, excuse me, 0.8 times 0.19. We need to also do the same thing for 0.58 times 0.68 plus 0.58 times 0.68. And here we go, it's not over, because bear in mind that you have a constant which is not written here, which is 1, and that 1 is going to be multiplied by W naught A. So the constant 1 should be included as well, so we need to add the 0.5 W naught A times 1. This is also important. And this is what we do, and we get this value here that you see 1.283, 1.2843, all right, which is obtained by taking x1, as you see here, x1 times, sorry, here we go. We have x1 times 0.61 plus x2, which is in red here, times 0.8, as we 0.61 times, so 0.39 times 0.61. So let me get back to this. 0.39 times 0.61 plus 0.19 times 0.8. So 0.19 times 0.8 plus 0.68 times 0.58. So 0.68 times 0.58 plus this 1 times 0.5. And this is what we get. We get net A as 1.2342843, excuse me, 1.2843, which is a combination function. We do the same thing for net B, as you will see. We do the same thing for net B. And how do we do that? We did the same procedure, but with the weights that are different. And then don't forget, we need to multiply by 0.71, 0.72. You need to take 1 multiplied by 0.72 for this weight. Then when we got these two, the next step is to do the activation function. And the activation function, as we saw earlier, it is equal to 1 divided by what? 1 divided by, let me just write it down here. 1 divided by 1 plus e, 1 plus exponential of x, and exponential of x becomes our input here, this value. Exponential of x is 1.2843. Here we go. So we have 1 over 1 plus exponential of 1, excuse me, this 1 multiplied is, I need to get rid of that. So we have 1 divided by 1 plus exponential of 1.2843. So this is what we've got here. And this is what, when we apply, we get this number here. When we do this, we get this number. So this is what I did here. We did 1 plus 1, 1 over 1 plus exponential of negative, excuse me, I forgot the negative here. Because, so remember the formula, it is 1 over 1 plus e power negative x. So 1 over 1 plus e power negative x. So we have negative x, negative 0.78. And this is what I did here. So 1 over 1 plus e power negative f9. Negative f9 is here, this one, this value here. So when I did that, I get f net A. I do the same thing for net B. It is 1 over 1 plus e power negative 1.5154. So this is what I get. And we are done. Our next step now is to get this net z. The net z is done by what? We do the same procedure. The same procedure is 0.9 times 0.783181 plus 0.9 times 0.81986 plus, don't forget, the 1 times 0.5, because you have this 0.5, a constant term here if you want. And this is what we did here. We got that. Okay, 1 plus 1, what we got here is this. Okay, so we have a 1 times 0.5 plus g9, that is this value here, times 0.9, as you see, plus this value here times 0.9, as you see, and we got that. The next step is the end, the final step. The first pass through the network is obtained by the output from the first pass through the network. The output from the first pass through the network is obtained by taking this value and replace it in that function. So you have 1 over 1 plus exponential of negative 1.94 12737. There we go. This is what we got, and this is our predicted output from these inputs that you have here. From these inputs that you got, this is our predicted output of 0.8746. Okay, so what we did is we just applied these different rules and formulae. Now, when we've got this output, you have to understand something, is that this output that we have obtained here is not necessarily the best option, is not necessarily the best solution. Why? Because these weights have been normally assigned randomly. So you add random values starting from 0 to 1, from which these weights have been determined. So these weights have not been determined through any specific procedure or anything like that. They are just random values that lies between 0 and 1 that have been set here. And these random values, they could be that they are very good, they could be that they are very bad at completely. So this result that we've got here does not indicate that we have the best result. It might be that this result is not good at all. Then what we have to do is that we might have to go through this network again. We might have to go through a second pass through this network with updated weights, with these weights that are changed now. These weights are not going to be the same as they are, but they might have to change in such a way that now this value is going to give me a more accurate, is going to be more accurate, because let's suppose the true value is 0.8. This is what we are predicting. The output that we are predicting is 0.874, but let's suppose the true value in the data set is 0.8 for that particular record. If it is 0.8 and you have 0.874, it means that this is not correct. There is an error that exists here. So we might want to improve that network in such a way that we get a better error. This error is going to reduce to 0. Let's suppose 0.85. We want to reduce this error to get it closer to 0.8. So then what we have to do is that we have to readjust these weights, as I just mentioned. By readjusting these weights, what we will do is that we will come up with a new fnet set that is going to be closer to 0.8 now. So this is what we are going to do in the next video. So for the first video, what we just did is we tried to understand, we tried to understand what a neural network is and how to obtain an output from a neural network by using the combination function and the activation function. And we did that using the sigmoid activation function. So the next step is to go and explain to you some of these different concepts that we call the backpropagation rule, also explain to you what a gradient descent method is, and so on. So we have done this part, and we are going to go forward in it by explaining you the sum of squared errors and so on. So what we did here is we just predicted an output through a first pass in the neural network using this data, using this information. A next video will follow.